Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Saufi bin Muhammad Zaini. I am currently a PhD student in chemical engineering, and my student number is 2021896062. And my supervisor is Dr. Sheikh Hassan from School of Chemical Engineering, and my co-supervisor is IR Dr. Sheikh Abdul Muttalib Al-Junaid from School of Electrical Engineering, UiTM Shah Alam. So this is my progress report presentation semester 2. So this is a little bit description about my supervisors. Both of my supervisors are very prominent in my area of study. Okay, so let's look on the introduction. The growing demand for portable electronic devices such as smartphone, tablet, drones, remote control, and etc. has induced the development of stable energy sources and efficient energy storage. Current commercialized lithium-ion batteries such as nickel manganese cobalt oxide (NMC) have a relatively low energy density to sustain the long running time of portable electronic devices. To pursue the energy material of inexpensive, durable, and high energy density, the lithium-sulfur batteries has gained much interest. Lithium-sulfur batteries are very promising technology. Lithium-sulfur batteries are based on commercial conversion chemistry, with sulfur being converted into lithium sulfide at the anode and lithium stripped and plated at the anode. The ability of sulfur to react reversibly with the lithium ions allows it to carry more charge density, which enhance the energy density of the batteries. In addition, as we can see here, lithium-sulfur battery has 6 times higher energy density than commercial NMC lithium-ion. This means that the battery in our gadget will be either smaller than lithium-ion batteries, or the same size battery would be able to last significantly longer. Despite their advantages, lithium-sulfur battery face numerous challenges, including highly soluble lithium polysulfide in the electrolyte that cause the shuttle effects. During the reduction process at the cathode, as you can see from the animated figure here, several reactions occurred. The lone change of lithium polysulfide, as indicated by the red ball, will form, and then it will detach from the sulfur cathode here and diffuse into electrolyte, and then migrate to the anode side with lithium at the anode. And the diffusion of lithium polysulfide backs and forth between anode and cathode will produce the shuttle effects. They will result in poor cyclic stability, low conductivity, and shorten the battery life. So our hypothesis is from this study the structural integrity of the sulfur cathode can be improved by incorporating activated carbon with sulfur as a cathode host, as you can see in the figure here. The morphology of the carbon structure and the surface properties of the cathode material play a great role in determining the performance of lithium-sulfur batteries. We believe there exists an optimal ratio of micro and meso porosity that contribute to the best performance of lithium-sulfur battery and trapping the highest possible of lithium polysulfide. The lithium polysulfide shuttle effect can be reduced effectively by modifying the porosity of the carbon-sulfur surface and absorption into porous carbon structure. Next, let's look on the objective of this study. First is to optimize the operational parameters such as heteroatom doping, chemical agent, and physical activation agent on the sulfur loading and polysulfide absorption using the Taguchi design of experiment. Secondly, to develop the kinetic model and absorption isotherm of the polysulfide absorption. And finally, to analyze the electrochemical performance of lithium-sulfur using coin cell types of optimum condition of PKS-derived activated carbon cathode. So, therefore, this project aims to study a new method of synthesizing carbon-sulfur composites from PKS and understand the impact of surface morphology on the performance of lithium-sulfur batteries. And our sub-research consists of three main sub-research, which are carbon synthesis and characterization. So this is the several analysis type of active carbon, and then it will undergo the optimization process using Taguchi method and analysis through linear regression, hazard ratio, and ANOVA, and then electrochemical performance analysis, which comprise of voltammetry, galvanostatic, and evidence spectroscopy (IES). So, the overall research methodology is shown here. It started with the crushed PKS will undergo a carbonization process with various type of chemical impregnation ratio. And then the carbonized PKS will further heat up by varying the activation temperature and doping ratio. The resultant product will be characterized to understand the surface morphology and surface polarity. And the AC will undergo the polysulfide absorption in the argon field glove box to understand the nature of polysulfide in terms of kinetic and acetone study. And the optimal parameter that is the highest polysulfide absorption will be used as a host for the cathode for further electrochemical analysis. And then the CR2032 coin cell types will be further analysis in terms of electrochemical analysis. Okay. Now let's look on the result. From ultimate analysis, it proved that the PKS is a suitable candidate for production of activated carbon cathode composite, since it has high carbon content, which contribute to the structural strength of sulfur cathode, and it has high nitrogen content, which is above 1%. The high nitrogen content is a crucial element for polysulfide inhibition. And as we can see from the SEM result, so for the raw PKS has non-pore observed. After the AC activated carbon, the PKS undergo several treatments such as temperature at 500 degrees and impregnation ratio 1, and using the potassium hydroxide, we can see that the micropore and mesopore structures are observed in this figure. This is a very crucial factor to track the polysulfide inside this porosity or the structural porosity here. This is my Gantt chart. So Alhamdulillah, I still in line with my my planning. So I am actively produce several types of active carbon using a various parameter, and right now I am characterizing. I am still characterizing the active carbon. Alhamdulillah. One paper has been published on the effect of different physical activation agent on the adsorbent pore development in recent innovation in chemical engineering, Scopus Q3. And one paper has been completed and under reviewing process, entitled the systematic review on the cathode development using biomass for lithium sulfur batteries. and the other 3 are still in progress. So this is my updated of my thesis writing. My introduction 10%, literature review 50%, research methodology 50%, and result and discussion 5%, and conclusion is not done yet. But I believe I will be able to complete all the thesis writing within the time. So this is my next semester planning. I'm going to synthesize and characterize the active carbon for objective 1 and objective 2, and completing the journal 3, writing thesis 1, chapter 1 up to 40%, chapter 2 up to 20%, chapter 3 up to 40% by March 2023, and start to write the journal 4 at the end of February 2023. So that's all for me. Thank you very much. This is the update for this semester from March 2020 to July 2022. So that's all for me. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.